Okay, so we'll go back to another video. So here we would like to verify a following identity involving the golden ratio number phi and some inverse tangent functions. We have that we want to show that 2 times the inverse tangent of 1 divided by the square root of phi cubed subtract inverse tangent of 1 divided by the square root of phi to the power 6 minus 1. Add that with the inverse tangent of the square root of 5 is simply just equal to just pi divided by 2. So that's a pretty long expression that you might be witnessing, and it probably leave you flabbergasted for some odd reason, probably with just golden ratio numbers and the inverse tangent function itself, and the radical functions too, including with the exponents. But there's actually a lot of properties involving with the tangent function itself. We'll actually be utilizing the double angle identity to make things a little simpler. And of course, because we have a golden ratio number, we're also going to be utilizing its properties as well to make the simplification nice. And it's also a nice little identity that involves the inverse tangents of its reciprocals that actually leads to an answer like this. So I said that being said, that's actually going to be the last step. But how we get to that last step is, well, the mystery that you guys will eventually see. So with that, why don't we actually jump right in? Let's actually start with our function over here, the inverse tangent of 1 divided by the square root of phi cubed. So let me actually first put this over here. Then this is 1 divided by the square root of phi to the power 3. So we note that for one that our golden ratio number are properties. We know that phi squared from the equations, from when you solve for the numbers, is simply rewritten, can be equal to phi plus 1. And then another property was that, so if I have also phi cubed, so that means that's also equal to 2 phi plus 1. Simply, I just add another phi over here, so I have that means phi squared and then plus 5, and then you could actually rewrite that and it lead to phi cubed. So in other words, that's the same thing. So when I replace phi with the value of 1 plus square root of phi divided by 2, in other words, that's also the same thing, can be written as 2 plus the square root of 5. So in other words, this can also be written as the inverse tangent of 1 divided by the square root of 2 plus the square root of 5. And so with that in mind, so now let's actually find its value specifically. So that means what I'm going to do is I'm actually just going to set this to some variable. We'll just call this u. So it just sounds like we're doing a u substitution again, or all over again rather. So what we have is we'll let u equals this following over here. So let me actually just put this under the brace. So u is equal to that. So in other words, that's the same thing as saying if I take the tangent of both sides, so that means tangent of u is equal to the value of 1 divided by the square root of 2 plus the square root of 5. So why don't we actually draw this little triangle, the right triangle, to see where the sides correlate with. So specifically, I have a right triangle over here, and then our angle is going to be u. So that means tangent of u is, of course, that's meaning opposite over adjacent. So that means the opposite is located at this side, and then our adjacent is going to be the square root of 2 plus the square root of 5. And so with this, we have our hypotenuse. So that means apply Pythagorean theorem, so 1 square, and then square this quantity, and then you take the square root of that afterwards to get this unknown side. So this is actually going to lead us to 3 at this, or the square root of 3 plus the square root of 5 over here. So with this in mind, so let's actually ignore the radical underneath this value for a second, focus on the inside. So I have 3 plus the square root of 5. In other words, we can write that as 2 plus 1 plus the square root of 5. And then in other words, that's actually going to lead us to the same thing saying as 2 plus 2 times 5. So let me actually write that in full. So 2 plus 1 plus square root of 5. Also the same thing as can be said as 2 plus 2 times 5. And so with this in mind, if I take the square root of both sides, so that means I have 3 plus the square root of 5, so square root of this quantity. So now if I just factor this out, so that's 2 times 1 plus 5, so the square root of 2, and then times 1 plus 5 over here. And then we just use this identity over here. 1 plus 5 is the same thing as phi squared. And if I use that property with the multiplication, so the square root and then times another square root, we have that this is just the square root of 2 multiplied by 5. Okay, so with that in mind, if we actually just go back to this triangle over here, so this is actually equals to, so if I draw the same triangle yet again, fix that, it just looks weird. So we actually just go back to the original triangle and actually just go back. So this is 1 square root of 2 plus the square root of 5. That was basically just from our earlier calculations that we did that. Instead that we just take the square root of that, just undo it, or rather do it the other way. So I have that this is the same thing as the square root of 5 to the power 3. And then our hypotenuse over here is going to be the square root of 2 and then multiply by 5. And so with this in mind, so this is great such that, and I mentioned that this is where we're going to be using, we'll be utilizing the double angle identity over here for the tangent function. So I'm going to write this over here. So we have that tangent of 2 times u. We know that this is simply written as 2 times tangent of u and then divided by 1 subtract tangent square of u. Okay. And so we already know we have tangent u, so we actually just put all these pieces together. So it's just in terms of, our golden ratio number then compared to what we have just from the simple, algebraic number, if you want to call it that perspective. Then we just put in the substitution back. So what I have is we can have this written as 2, and then we set that tangent u. So of course, I just put this as, this is going to be 1 divided by the square root of phi cubed. And then being divided by, so this is going to be 1 and then subtract, so tangent square u, so it's just square both sides. So that means what I have that this is going to be just 1 subtract 1 divided by phi cubed. And then what I'll do is let's actually simplify this further such that let me actually multiply a phi cubed to both the numerator and denominator just to get rid of the fraction over here. So putting this all together and then you simplify that out and you get this in terms of, the same base exponent fraction, etc. Well, we have that this is going to be 2 times the square root of phi cubed and then divided by phi cubed subtract 1. All right, so with that in mind, let's actually now go into a deeper expansion for phi cubed over here. So let me actually go into a different marker for this. All right, to further expand this, so phi cubed to subtract 1. So we can actually decompose this as phi subtract 1 and then multiply by phi square plus phi and then add this with 1. Okay. And so phi minus 1 has that nice identity, is actually going to equal to the reciprocal of the golden ratio number. So 1 divided by phi. And so I have phi square over here, so I can actually replace that with phi plus 1. And then I have, doubled for each of those numbers, so it's 2 phi and then add that with 2, so 2 phi and then plus 2. So of course that I can factor out the 2, so that means that I'll just change that to 2 divided by phi. And so I have phi plus 1. And then in other words, that's actually if you phi plus 1 and then replace that back with phi squared, so that means that just cancels out the phi. In other words, this is going to be the same thing as 2 phi, and that is actually equal to the same thing over here, so we can actually do that bit of a substitution like that. So just to reiterate all that, so in other words, we have that tangent of 2u, which we said that was equal to, so actually substitute this back into over here is what I meant to say. Substitute the 2 phi back to the denominator over here. So to reiterate, tangent of 2u, in other words, in terms of the golden ratio number, there's going to be 2 times the square root of phi cubed, and then I'm substitute this back over here, so 2 phi. In other words, that's actually just simplified down, get the exponents, in terms of the exponents of the base or fraction rather. And then I have that this is the square root of phi. And then that actually just leads us back to, if we actually just take the tangent of both sides, so back to what we originally started from earlier, then we have that this is actually the same thing as tangent of 2 times the inverse tangent of 1 divided by the square root of phi cubed. And so, well, let me actually just box this for now. We're not done exactly, but that actually just verifies one of the things. So with that, but in other words, well, I don't have to box this because, not just yet, because what I can do is actually just take the inverse function of both sides. So that way that actually just gets rid of that tangent, just because it's simply just starting from what we have from earlier and then leads us to this conclusion. We have that, if I take that, that means this is going to be 2 inverse tangent of 1 divided by the square root of phi cubed. That's simply just equal to the inverse tangent of the square root of phi. Okay, so with that in mind, now I can actually box what we have so far, just like that right here. Okay, so that's actually one of the identities written down. So we can actually now continue forward, specifically going to our phi to the power 6 minus 1. We'll ignore the radical in just a sec. Okay, so moving forward, so specifically we have our phi to the power 6 minus 1. We're just going to look at the denominator here and ignoring the radical. So let's actually decompose this. So phi to the power 6 subtract 1. We can decompose this as the following. So I have phi cubed plus 1. So it's like a difference of squares, but you know, instead it's the cubic exponent. And then phi cubed subtract 1. Okay, so with that, we can actually decompose this even further. So what I have now is going to be phi plus 1, then multiply with phi square, subtract phi plus 1, multiply with phi subtract 1, multiply with phi square plus phi, and then plus 1. This is kind of similar to what we were doing just from earlier over here. So some things we can actually reduce this down to. Phi plus 1, we have that's the identity of phi square. And then phi square minus phi plus 1. So what is it? I have phi and then subtract that. So that means that just going to leave us with multiply by 2. This one is, as I said earlier, this is the inverse reciprocal, the reciprocal of the golden ratio number. So 1 divided by phi. And then over here, phi square plus phi plus 1, we can reduce that. That was actually the same calculation from earlier. That's the same thing written as 2 phi plus 2, but we can also reduce that to say that that's the same thing as 2 times phi square. And if you simplify this, I have 4 times phi cubed. Okay, so now that has to mean that, of course, that's equal to phi to the power 6. So that means, of course, I have to take the square root of both sides in order to get that denominator what we're doing. So to the conclusion over here, I have that the square root of phi to the power 6 minus 1 is simply just equal to 2 times the square root of phi cubed. And we'll say that in 3 triangles or 3 dots, I don't know why I said triangles. Let me actually put this in a different marker for that, and I'll box it in the black. We can actually deduce that the inverse tangent of 1 divided by the square root of phi to the power 6 minus 1 is simply just going to equal to the inverse tangent of 1 divided by 2 times the square root of phi cubed. And so that is our identity that we're actually going to be working with / saving for later until we can actually get to the bigger picture of what we're really dealing with. So with that in mind, there's still some things we still have to calculate and reduce down to. So I'll leave you guys to look at this for a bit, and afterwards we'll actually continue forward. Okay, so I just want to reiterate what we have so far, the identities from earlier that we deduced to. Of course, it's not exactly showing that we've lead to the right-hand side, but these are actually, you know, helpful, you know, tools that we actually will be using, come in handy, like, eventually. So with that in mind, so let's actually continue forward and write down for what we have is that 2 times the inverse tangent of 1 divided by the square root of phi cubed. Then if I subtract this, so this is basically just rewriting these 2 expressions first. So then 1 divided by the square root of phi to the power 6 minus 1. Okay, so with that in mind, so let's actually now just reduce this to say that we actually just put in back those following identities. So I have that the inverse tangent of the square root of phi, and then this is subtract with the inverse tangent of 1 divided by 2 times the square root of phi cubed. Okay, so with this in mind, so why don't we actually start off by actually taking the tangent of this entire expression over here. So that means, so tangent, and then same expression over here. So let me just write this out in full. So tangent, and then we have of this entire expression just from below. So of course, I'm pretty sure you've seen a tangent identity like this. What we'll be actually using is the tangent identity for the difference of 2 different inputs, which is written as follows. So tangent of sum A subtract B is simply just going to equal to tangent of A and then subtract with tangent of B, all this being divided by 1 plus the product of tangent in A and then tangent of B. So this is also pretty great since I have a inverse tangent, so just putting this back in, we're instead just going to leave us back with just the input itself. It's just undoing everything. So putting this all together, so what we have that this is actually going to be, so let's see, tangent and then square root of phi and then this input. So we have the square root of phi and then subtract 1 divided by 2 times the square root of phi cubed. All this being divided by 1 plus So this is going to be the square root of phi, and then multiply by 1 divided by 2 times the square root of phi cubed. Okay, this looks like a lot to intake over here, so how about we actually, in order to get rid of these denominators over here, let's actually just multiply a 2 times the square root of phi cubed to both the numerator and the denominator. At least this way, this actually just gets rid of the fractions from below from both our numerator and denominator. Now to continue forward, if we perform that multiplication out, what we have is now the fractions disappear, the rational numbers, put it that way. So that will lead us to have 2 times phi square, at least that just undoes that out because of the exponents, how you write it. Then subtract 1, and then now being divided by 2 times the square root of phi cubed, and then add this with the square root of phi. Okay, so there's some things, as you can see, that we can actually reduce this even further, such that I can actually, for one, phi squared can be substituted. I already erased it, but that's the same thing as phi plus 1. So 2 times phi plus 1, then subtract 1, all being divided by. So let me also factor out a square root of phi over here. So that means what I have is that this is actually going to be, so factor out the square root of phi, and then taking it another step ahead is that I can actually just replace this. So we have the following input of 2 times phi, and then add this with 1. Now, if you actually see that if I perform the addition, so 2 phi plus 2 and then minus 1, so that's 2 phi plus 1, that actually cancels out from both the numerator and denominator, and then that just leaves us with 1 divided by the square root of phi. Okay, so with that in mind, we can now continue to say that, let me actually move on to a different marker for this one. So that thus reiterates back to over here. So let me write it over here. So tangent or inverse tangent of the square root of phi. And also keep in mind, remember, we took the tangent of this. So the tangent of this input is equal to this. So we're actually going back to the original of what we have earlier. So this line over here specifically. So minus inverse tangent of 1 divided by 2 times the square root of phi cubed. So that just leaves us to say that this is actually just going to equal simply just the inverse tangent of 1 divided by the square root of phi. And of course, with this is actually the same thing as just the above equation. So 2 times inverse tangent of 1 divided by the square root of phi cubed, then subtract the inverse tangent of 1 divided by the square root of phi to the power 6 minus 1. So this is equal to that. So this is the same thing as just before. So let's reiterate this a little even better. So our box over here is just that is what the conclusion has come down to. So that means this actually makes things a lot more simpler, because if I actually just replace this back for this entire thing, so what we really have is that, right here should be good. So over here, that means I have that so far, this is going to be the beginning. So what we just substituted, and then this is our new substitution over here, 1 divided by square root of phi. So 1 divided by the square root of phi, and then add this with the inverse tangent of the square root of phi. We're actually done, because that actually equals pi over 2. And this justifies that, because our nice little identity for the inverse tangent data, as I said, is the reciprocal of the sums. So the inverse tangent of x, add this with the inverse tangent of 1 over x, is simply just equal to pi over 2. And of course, this is for the conditions such that x is strictly greater than 0. If it's less than 0, then it's actually reverses the opposite direction of that. So our identity is over here, and that actually completes the proof, or the verification of that identity over here, that this is actually equal to pi over 2. So we actually did all this substitution over here that it came down to, from this original for these first 2 terms, came down to this value. You add that, you add this and this value together, and it actually utilizes this identity over here just such that this actually just simply just equal just pi over 2. Nice verification involving inverse tangent function and the golden ratio number. A long one, but a very beautiful one indeed. So yeah, that's pretty cool if you ask me.